Boyle's law tells us about the relationship between the volume and pressure of a gas. It's important that we learn about Boyle's law because it's the underlying principle of how we breathe and why our lungs take in oxygen. It's also significant for the design of engines, and it helps us mitigate the risk of explosions as we understand the behaviour of gases under different conditions. Now, the volume of a gas is pretty straightforward, but what is pressure and where does it come from? So kinetic theory tells us that the pressure in a gas comes from the atoms and molecules inside the gas hitting the walls of its container. So let's have a think about how that pressure would be affected if we were to increase or decrease the volume of that gas. So let's say I have a volume of gas here. Now, if I were to increase the volume, the molecules will be spending more time on the inside of the container rather than interacting with the walls because they've got so much room to do that. So high volume, low pressure. And conversely, if I were to squeeze the gas and reduce the volume, now the atoms and molecules will be spending more time at the walls because there's less room for them to move around. So low volume, high pressure. And it's this inversely proportional relationship between pressure and volume, which is Boyle's law. Now we can prove Boyle's law using this piece of apparatus, and this unit is particularly nice because it doesn't require any setup, and it's going to give us lots of nice data points to model that PV relationship really accurately. On top of that, practically, we have a battery pack at the side, so you don't have to plug it in anywhere, and it's small and compact, so it's super easy to store. With Boyle's law being the PV gas law, we need readings for both pressure and volume. So we will get the volume measurements using the graduations on the syringe on the front of the unit here, and we'll get the pressure readings using this pressure sensor, which has got a digital readout on this display just here. Now you will also see that the pressure readings will be in kilopascals, so it's a nice easy conversion to get it into SI units. You'll also see that the unit has got sockets here to connect to either a data logger or a big demo voltmeter. So if you wanted to turn this into a class demo, it has the capability. A quick demo of how this unit works: we turn the unit on, and then you will see the pressure reading change as I change the volume in the syringe. Now, it's as simple as that. So let's get this unit ready to take a full data set and we can plot our lovely graph. So we switch the unit on, and if I pull the syringe and detach it from the sensor, now that sensor is just sampling atmospheric pressure, and it thinks that it's at 99 kilopascals. The typical value you'll see for atmospheric pressure is about 101 kilopascals, but remember that's at sea level. Now I'm filming at Keele University, which is on a little hill in England, so this value for atmospheric pressure is about right for my elevation. Now when the syringe is separated from the sensor, we want to pull the plunger out to about the halfway mark. Now we do this because it means that we can use the full range of the syringe and it won't saturate when we get to small volumes. So let's push it onto the sensor and let me show you what I mean by that. Push it back on. So the sensor gets saturated when we get to very small volumes. So what I mean is that it will max out. So we just want to make sure that we can use a good range of the graduations along here to get lots of data points for our graph. Okay, so it looks like the smallest volume that I can do, and it's going to give me a nice reading, will be probably that one. So what I'm going to do is I'm going to make sure that the tip of the plunger, that first ring on the plunger, lines up with the graduation on the syringe. So it's going to be about there. So that's going to be my first data point. So it's two of these minor graduations, and we can see that that is 0.5 milliliters. So that's going to be 0.2 milliliters for that first reading here for volume. And that's going to give me a pressure reading of, can I be stable enough? 167.2. I've written those first values down in a table, so to get my next reading I need to go to the 0.3 milliliter mark on the syringe and write down the pressure reading off the digital display. For further readings I just need to change the volume by 0.1 milliliters every single time and note down the pressure reading at each volume increment.
So I've run through the entire experiment and here is my final data set. In column A and B, I've got my pressure in kilopascals and volume in milliliters, and I need to convert everything into SI units for the plot. So in column C, I've got pressure in pascals, and you can see that I've got this value by timesing my pressure values by 1,000. You'll then see that I've added 0.2 milliliters to each of my volume readings. Now there's a prompt to do this on the front of the Boyle's law unit, and this is to account for the internal volume of the sensor and the connecting tubes. So this is an important step. I then need to get my volume in meters cubed. So to do that, I divide my volume readings by 1,000,000, and then I need to take the reciprocal of that volume. To plot, I need to put pressure in pascals on the y-axis against 1 over volume in meters to the -3 on the x. And you'll see that we get this lovely linear relationship between pressure and 1 over volume, just as we expect from Boyle's law. I've told Excel to display the R squared value on the chart, and this is a representation of how good the fit is. And you can see that it's really close to 1, which shows that it's a good fit.
So there we go, we have confirmed Boyle's law. Now, if you want to see other ways that you can simplify practicals for your classroom, please see our other videos. Thank you very much for watching.